So for those who don't know me, or maybe you don't remember me, I am Andrea. I am a PhD student at the University of Pisa, and I'm also an associate researcher at the CNR, the National Research Council of Italy. My background is in social science, but I'm doing a PhD in AI. So over the past 3 years of PhD and also my master's, I've been studying how to apply mathematical models, but also computational approaches to the study of specifically social networks, but also different kinds of networks that I will show you today. My goal with this class is, of course, to provide you with a very, very tiny bit of background so that we are all on the same page on what networks are and how you can manipulate them and analyze them. But also, my main goal today will be to show you the beauty of working with networks. This might sound a bit silly or maybe a bit stupid to you, but the idea here is that with networks are a particular kind of data. You can do so much with it and uncover in very simple way, uncover so much information that you could not otherwise with other models or just with tables and so on and so forth. And what I've learned to appreciate about networks is that they give you an insight on human behavior or whatever behavior of the subject you're studying that you cannot get otherwise. So I would be particularly happy if by the end of today, when you close this and you're very tired and you go and have dinner, if I made you understand just a bit how beautiful working with network is, then I will be very happy with the job that I've done today. So very quickly, all the material that I will show you today is available on this link. Sorry about that. Let me also paste it in the chat just in case. But you don't really need to follow it. I've also asked Sumaya later to share it with you by email. The idea is just that I'm providing you the slides. So if you want to read later, I'm providing you the slides. I'm providing you links to additional materials that you might want to explore later. The page is this one, not this one, sorry. It's this one here. And yeah, very basic description of what we will do here. The slides and the notebook that we will see. So we will see some Python code as well. And also a tool that I will show you, it's called the Gephi, which requires no code, and it will cover 99% of your, in general, of social scientists' needs with networks. Additional materials like books and more, like this is a technical book, but it's very easy to understand. And also these one are recommended reads that are very divulgative, very easy to read, very nice narrative books. Okay, so just this is again not really important to follow along, but just in case you need it after this class, you have the material all there. Okay. So let me just skip this presentation. You already, most of you already know me. Just a quick context. I am member of the KDD lab at the CNR. This is the research unit that works with network science. The idea is that we model the world by the means of networks, and we use these very powerful mathematical tools to try and understand something more about human behavior. We do this by studying mostly social networks, so specifically networks that we extract from social media. but also some of us study cognitive networks. So there is a way of extracting networks from text, for instance. So for those of you who attended the winter school, the YADESA Winter School in February, you have seen how to work with text. But now with this text, with the information that you can draw from text, you can also build the networks. And these networks are not meaningless. These networks will provide you tools, for instance, to analyze, I don't know, word relevance or writing styles, or if you are into linguistics and you work with syntactic trees, those trees are also kind of networks, okay? So there are a lot of, what I will show you in a bit is that networks are really everywhere, okay? So this is what we do. We try to apply this model to a variety of different contexts and develop methods to work with them. So why should we care about complex networks? First of all, what is a complex network? Again, this will be a brief introduction theory part, and then we will move to Python. And after Python, we will do something that, since it will be late, we will do something that is more easy and use software that does not require to code. Okay, so again, now I show you very basic principles of theory in network science. Then I will show you in Python how to work with networks. Again, I won't need you to memorize the code, just to trust that it works. And then everything is very well documented online. And also you have Gemini, as you know, that can help you to write code for you. And finally, we will see this software that will provide a very good visual representation of networks and also some statistical analysis as well. So why should we care about complex networks? First of all, what is a complex network? So a network, you see it on the screen, right? On the bottom, you see this kind of these dots and these lines. This is a network, okay? So this is a visual representation of a network. What makes it complex? So if you know about complex systems, a complex system is a system. So it's a compound of a lot of tiny objects that interact, and this interaction produces some behavior. What does it mean? Think about when you go to work in the morning, you get in your car, and even if you don't really like your job, you want to go to reach your job destination as quickly as possible, right? Nobody likes traffic. So you know the route, you know the street that you have to drive through, and you take the shortest possible route to get there, usually, okay? So the problem is that everyone does this, okay? So you do it, your colleague do it, everyone else in Istanbul or in any other city in the world does it, and this produces exactly traffic. So traffic is an emergent behavior of a complex system that is the city road network, okay? So you have these people that move around, and they have a very specific goal, but this very specific goal produces an effect that does not depend on my action. It does not depend on your action. It depends on, I would say, the compound effect of all the actions that we take, okay? So this is basically the idea of complex systems. Complex networks are very large networks that are used to study complex systems. So behind each of these systems, there is a network that defines the interactions between these components. And again, if you're wondering about complexity, there is a very nice pamphlet here. It's also available in Turkish. This Complexity Explained project, which tries to explain what complexity is. Here you can find it in Turkish as well, but also in many other languages. It's a very brief read of like a couple of pages. By the way, this is not sponsored. Everything I'm going to show you is free, and you can find it freely online. But you can find a lot of these kind of things online, okay? So the idea is that complexity is something that as social scientists we should study. See here what Stephen Hawking said. The 21st century is the century of complexity. Complexity is all around us, and networks are one of the tools, perhaps the primary tools that we can use to analyze them. So networks are everywhere. And once you start looking at networks and searching for networks, you can find them everywhere. Maybe you don't know it yet, you don't know it already, but once you leave this class, if you look around you, you will see networks really everywhere. So here, just very simple networks, you know, your friendship networks where nodes are, you know, these kind of dots, you know. Nodes are individuals and links are social relationship. Then you have the scientific collaboration where you have researchers linked by co-authorship. So we co-author a paper together, we are linked in this co-authorship network. Actor connectivity between actors in movies. So if two actors are connected, if they worked in the same movie. Communication networks, phones and with phone calls, airports and flights, and so on and so forth, okay? Again, technological networks, the internet is a network, okay? So you have a lot of computers all around the world that are connected. Scientific citation, biology. Biology is full of networks, okay? Think you've heard probably of neural networks, okay? So neural networks are a specific kind of network. Artificial and biological neural networks are both, of course, networks, and it can be studied with the tools that we see today. And also mobility, what I told you before, you have cars, you have transportation means like buses, trains, and so on and so forth, and that becomes eventually a network. So the data availability of the past, I would say 20 years and more, has allowed us to study a wide variety of networks. And indeed, most of the, like many of the recent, I would say, discovery, breakthrough in different sciences are built on networks. So here, I'm just listing some of them, but if you think like, of course, the web, okay, the internet, okay, so or actually the web, so the network of pages that you browse through with your browser, okay? If you think about metabolic networks or protein-protein interaction networks, okay? So again, I don't want to be boring, but networks are really everywhere. And since 2008, we have online social networks. So we have this kind of networks, social networks that are built digitally, and they evolve, and we can study them, we can access them online. So network theory, what we will see today, is a compound of graph theory and a lot of other branches of science, okay? So it's really a multidisciplinary field, and you can study basically, you can apply this again to any field that you are interested in. Most of the, what's happening? Sorry, okay. Can you still see my screen?
Yes.
Something, okay, no, maybe something went wrong on my end. Okay, so the idea here is that you can study with tools that come from graph theory, which is basically mathematics, but also statistics, computer science, physics, biology. These ideas from these different sciences come together in network science, network theory. And some of you might know this guy, is Immanuel Kant, very famous philosopher. So if you're into ethics, he was probably the most renowned philosopher and also contested philosopher in ethics and morality. So this guy, Kant, lived in Königsberg, and the bridges of this small town is basically where network science was born. I don't want to bore you with the history of network science, but this is a very nice intuition of what networks can do. So people in Königsberg had this they tried to do this thing. Okay, so this is an island that is in Königsberg, and this island is connected by these 6 bridges. Okay, so you have this all these kind of these parts here, and people in Königsberg played a game where they tried to pass through all the bridges exactly once. So you have to pass through all the bridges, but you cannot pass through the same bridge twice. And a very famous mathematician, Euler, in 1635, so around when Kant was living there, he discovered, applying for the first time mathematical modeling, a graph modeling, a network modeling of this situation that you see here. He studied and he postulated that this cannot be done. You cannot pass through this exactly once, because he explains that if a graph has more than 2 nodes of odd degree means the number of connection, there is no path that crosses each bridge exactly once. Sorry. So the idea is there is some mathematical properties that we can extract that can tell us something about the network that we are studying. Of course, this is a very simple example. It may not tell anything to you, but these kind of mathematical intuitions apply all over, again, in many scenarios. So now we will go through very basic measures. There will be some equations in the slide, but you don't need to learn about them. I will explain this in very simple terms. And again, it's not important that you memorize. It's just that if I say later, we will compute the degree, you have to know that a degree is the number of connection that a node has. That's it. If you have any question at any point, you can write in the chat, or maybe you can unmute yourself. I'm not sure you can do that, but there will be a way you can interact with me and interrupt me and ask me to clarify things. So networks are basically the real system, okay, that I want to study. So my social network, so the people that I connect with, are what I call a network. And the graph is the mathematical object that I use to model this network, okay? So I would say that network is a reality, and the graph is a representation of reality, okay? Networks are these kind of things here, right? Where you have nodes and links that are connected, that connect these kind of nodes. And the first distinction is that you can have undirected graphs, or where links are symmetrical, or you can have some idea of direction, okay? So you have co-authorship links. If me and you co-author a paper together, there is no direction. We are just connected. If we are in the same room, we are just connected. There is no direction. But if I'm talking to you, there is a direction in the way that maybe I'm calling you on the phone, okay? So there is a direction from my phone to your phone, okay? And this enables different properties that you can study, okay, depending on directed versus undirected networks. Node degree, we have already seen this. You have basically the number of links of each node. So for instance, this node here, A, only has degree 1, okay? Because it is connected only to one node. And when you have directed graphs, of course, you can have a degree of, like you can differentiate between the edges that go out and the edges that go in, okay? So you could have an in degree, so the number of edges that go in through that node. So this C node will have in a degree of 2, or you can have out degree. Out degree would be, in this case, just 1, because you have only one thing going out, okay? Again, the idea is that we call degree the number of connections that a node has. This is very important. And what we study about networks is maybe we study the distribution of these degrees. Okay, the distribution tells us something very important. What is a distribution? Don't be scared, please. Don't be scared. This is not. I don't want you to delve into the mathematics. The idea is that I study how many nodes have a certain degree. Okay, so in this curve here, you see that this k is the degree. So you have nodes that have degree 1, and you have nodes that have degree almost 100, something like that. And this is the fraction of nodes that have this kind of degree. Okay, so what does this figure tell us? It tells us that most nodes in almost any network, most nodes have a very small degree, and very few nodes a very high degree. So this is called a rich get richer effect. Okay, the idea that if you are familiar with the 80-20 rule, this is called differently across various disciplines. The idea that a few elements are responsible for a lot of, are responsible for most of the effects that you see in the data. So I don't know, the top 1% of the richest people in the world hold like 80% of the total wealth in the world. Okay, so this is kind of the same thing. If you think about influencer on social media, those top I don't know, 10% of people, they have most of the connection that you can see in social media. And this applies to everything, okay? Website visits, for instance. You visit Google way more often than anything else. So Google will be here, okay, in a hypothetical network. Once you have defined your network, you can study paths. And this is very important. Paths are basically, the steps you can take to go from one node to another node, okay? You can care about direction or you cannot care about direction. Of course, this changes things. But paths are something that are very important when you model network because, for instance, if you think about virus spreading, okay, epidemics. So during COVID, what we were trying to do was to try to predict the people that were at risk of having COVID. Okay, and how do you do that? So you build a social network of real contacts between real people, and you consider the direction, and then you say, okay, let's say I am a virus and I start from A. So when A meets B, the virus can pass from A to B, okay, and then can pass from B to C, and so on and so forth. So okay, again, there is this idea of a path of the steps that something along the network can take. Paths are related to distances. So again, a distance between two nodes is basically the length of the path. Very easy, nothing too complex. By the way, if I'm going too fast or too slow, let me know. Again, this is just the very basic, and then we will just move to more practical stuff. Again, you have the degree, that is the number of connection, the path, that is, some steps you can take, some route you can trace in your network. And then this is density, which is basically the proportion of edges that exist over the edge, the proportion over all the edges that could exist in the network. So if you take one node and you connect it to all other nodes, that will have the highest density. But most networks have very low density. If you think about a social network, it is not true that all nodes are connected to every other nodes, okay? So maybe locally, you are connected to a lot of your friends and your friends are all connected among each other. So you have a local density that is very high, but a global density that is very small. So, if you think about all the people in the world, it is not true that you are connected to all 8 billion people in the world, but it's very likely that you are all connected to maybe most of the people in your department, okay? There is a way of computing the importance of a node in a network. This is misleadingly called centrality, but I don't like this term, the idea of being central. It doesn't mean anything, okay? But there are different ways that you can use to compute the importance of a node in a network. So the degree, for instance, is what you have seen so far, is how many friends, how many connections does a node have. Another one is PageRank. For instance, PageRank is an algorithm developed by Google that was used to discover important pages on the web, okay? This algorithm can be used and applied to all other contexts and basically counts how many important interactions do you have. Another one is closeness, that it tells you what is your average distance between the rest of the network. So let's focus on degree and closeness. So degree tells us how many friends, how many connections, and closeness tells me what is my distance from me with respect to the rest of the network. I'm well connected to, is it easy for me to reach all of the network, or is it hard? Do I have to do a lot of steps or not? So most of these are correlated, which means high degree will probably lead to high closeness and so on and so forth. But depending on your question, on what kind of data you are studying, maybe you're studying, I don't know, trade networks, where you have countries that are trading some goods, or you have peace treaties or something like that, and you want to study the most important country in that specific field, in that specific area. So there are several ways of defining importance. So you will have, again, degree, and these are some of the most popular, but there are hundreds of measures. This can be overwhelming, but most people just use some of these 6 that I'm showing here. Let's go quickly. This is a very simple idea of how to apply social theory, anthropological theory to networks, or rather apply networks to prove some anthropological theory. So if you don't know about Dunbar is an anthropologist. I think he's still alive. If not, he died just a few years ago. I'm not really sure. But he postulated this social brain theory, that we have a cognitive limit of 150 people. After 150 people, we cannot sustain contact, okay? So most of the people you know, if you count in your mind all the people you know, you will likely not go beyond 150 unless you do a lot of effort. And this is a cognitive limit, because our brain apparently cannot maintain social relationship with more than 150 people. So what happens is, with networks, we can show that this is true. And we can also show that there are different degrees of importance of edges. So you will see that most of the people that you know, that you are like the first people that you will remember in your mind when you count all the people you know, are your family, okay? Your very close friends, with which you interact a lot. Then there is other people that live in your city, people that do your job, something like that, and then distant relatives, people that live on the other side of the world, maybe someone who you met on vacation once, something like that. So this idea that there are different levels, different strata of connections that you can have. And network science can study this. So, for instance, these guys studied it on Facebook, and they find out that there is a minority of people with which people do a lot of interactions, and then a majority of people with which you are just connected but don't really interact. Other things you can do with networks, and then we will move to the applied part, is identifying communities. So think about your friends. Okay, you will have maybe your childhood friend that count as a kind of a community. Then you will have your friends from a university. Then you will have, I don't know, friends from a job that you used to have some years ago, something like that. So all of these are different communities. Some of these communities could also overlap, means that some nodes can be in multiple communities. But the problem is, what is a community exactly? Well, this is a very good problem, and there is no solution to this. There is no accepted definition. I mean, social scientists like this stuff. There is no one true thing that is always true, okay? It depends on the context. But in general, you can have this intuition that a community is a set of entities, where these entities are closer together between them than they are with the rest of the network. Again, this is not, it may not always be true, but there is this idea, this sense of groups that emerge in the network, okay? A set of nodes more tightly connected with each other than with nodes belonging to other sets, to other groups.
Andrea,
And there are, yes?
sorry, we have a question on the chat.
Of course.
So, I mean, if you raise your hand, I will let you know to unmute. But Suhail is asking, can you kindly explain the degree of edges again?
The degree of edges, of course, yes. So in networks, we have this kind of situation here. You have your nodes and you have your links, your edges, okay? Nodes are basically your entities, the things that you're studying. Could be people, could be, I don't know, cars, could be proteins, everything, whatever you need, whatever you're studying, what your object of study is, that's probably gonna be nodes. Then you study the interactions between them, okay? The interaction between them, we encode these as edges, okay? So you have these lines here. The degree of a node is simply the number of links connected to the node, okay? So this node A here will have a degree of 1 because it only has one connection. While this node here, B, will have a degree of 4 because we'll have 1, 2, 3, and 4, okay? This is the most basic quantity in network science. You have a node and you count how many connections it has. That's it. So if you add the information on the direction, then you can distinguish between the number of connections that go out, okay, from the node to other nodes, or the number of connections that go in, so from other nodes to my node. So again, you have this degree of nodes that is the number of connections in general. But also you could have in directed networks the number of edges that go out to other nodes, or the number of edges that go in my node. So if this is a social network, this guy only has one friend, okay? While this guy has 4 friends. The number of friends of my node is my degree. I hope that now it is more clear. Let me just go back to the chat and see if... Okay, that's great. So sorry if I'm moving fast because I thought that you would be more interested in practical stuff again. But again, if you have questions or anything, just place it in the chat and eventually we will come back to you. So the idea of communities is that they are these groups of nodes that are very closely linked together. And you can see this is very ugly visualization of a network, that this is a social network from Facebook, that you have a lot of these kind of groups, okay? So these groups, these nodes are all very connected together. They are not connected to guys from this other group, okay? So this is one way of defining a community. And we will see that there are a lot of algorithms. You don't need to memorize them, but there are very good references that I will leave to you in case you're interested in community analysis, community detection, so that you can select and use the community algorithm that best suits your needs. We will see this in a bit, but real-world networks, like very large networks, are too complex to be analyzed visually. And that's why we will study Python as well. But in my experience, unless you are studying like networks with 10,000 nodes or more, most of the time you can visualize it and extract some information from them. Most of the networks that you will analyze are not really going to be that large, unless you study, for instance, road networks or social media or something like that. But if you study, I don't know, interactions between different countries, well, there are only so many countries in the world, okay? So it's not a huge network, okay? Another very interesting thing is this that you can study is whether nodes with certain characteristics are connected together. If you think about your best friends, well, if you're a woman, you are very likely that all or most of your friends are women. And if you're a man, well, all or most of your friends are men. Of course, the opposite can also be true. Well, in my situation, in my case, for instance, I think I have more women friends, but again, in general, this is an exception. This sociological principle, the idea that birds of a feather flock together, or that similarity breeds connection, okay, there is this idea that there are some characteristics in our maybe their demographics, maybe their interests, whatever. There are some things that as humans we are more prone to connect with other people with the same characteristics, okay? And there are some measures that you can use on networks. You take a network, you compute some measure that we will see to see if a network is very well connected and assortative, meaning that nodes with the same label, with the same characteristic, are connected more than others. But in many very large networks, again, this is why networks are complex for visual analysis. In very large networks, you will have like some areas where nodes connect together with the same label, some areas where nodes connect together with different labels. So again, there are different characteristics of a network, and sometimes one number is not enough to describe the complexity, again, of a network. But what we will do today is see some very simple measures and interpret them and try to understand what they tell us about our data, so that you can apply those to your data set that you might want to collect. What we can do with networks, this is what we do with networks at the CNR. We study, for instance, the migration of people around the world. So if you think of people migrating, it's people that are moving along a network of cities or of countries, okay? If you think about the web, the social media especially, you have these people that share information. So you have a social network, and you have information that travels through the network. The post, the link with news, okay, and fake news. So specifically, what I do in my research is try to study these kind of online social networks and try to prevent the diffusion of networks. So of fake news. Okay, so how can I use the information of the structure of the network to block this diffusion? What are the most critical nodes, the most critical parts of my network that I have to safeguard? Okay. Signs of success. So there are people who are studying networks of, these are football players that pass the ball from one player to the other. And this is they extract some measures that tell us how good these players are. Okay, and this is used to forecast the outcome of football matches. So there are some very good models that can tell you, there are some people who bet on these things, that bet on sports. People who bet on sports, these kind of how to say, the money that you make, that when you bet, depends on past networks of passing networks. What does it mean? That when you bet something, if this guy is considered to be very strong, depending on his network, and you bet that he will win, then you will get not a lot of money because the network says so. This is a kind of a thing that networks are used to. I'm just referring to this because in Italy we have a very big gambling problem, so we try to explain this kind of situation here. But also you can forecast the success of startups with these kind of network models. And again, urban mobility, you can study the flow of people all around the city, and also you can study how to best plan a city. There is this idea of 15-minute city where all the most important things in a city are located within 15 minutes walk, something like that. So, okay, I think we are done with this theory part. Before going to the more applied part, I just want to check that there are no other questions. And if there are questions, please tell me. I will be happy to answer. So the idea here is that we have some mathematical tools. Networks are essentially a tool from graph theory, which is mathematics. And we apply this to a variety of different concepts to understand something. And the very cool thing about networks is, again, we have seen that in social networks, a few nodes have most of the connection. So influencers are very, very well connected compared to the average user. And this is true for social networks, but for some reason, for the beauty of complexity of networks, it is also true for power grids, for, transportation networks, airports. A few airports are connected to most of other airports in the world. Okay, so there is this property is which you study on one network is ubiquitous. You can study it, you can find it in everywhere else. So for instance, let's think of a crazy network where you have elements of or people that appear in the same document together. So people who appear in the same document you will also have very, very cited people, and very few, most people are not cited. One thing that I wanted to show you, you might have heard about the Epstein files. So very briefly, this is a very large scandal. Basically, most of the rich people in the world have been doing very bad stuff, and now there is a lot of documents that prove that they have this kind of connections. And some people, what they did was basically draw a network extracting all the dimensions of people in these documents, these Epstein files. Okay, so you will have this kind here, Jeffrey Epstein, which is like the main guy, who a lot of other people are connected to, and then think of what simply with the measures that I have showed you, density or degree. Think about the things you can do to understand more about this network. So simply, this is not really a network in the real world, right? These are documents. But if you take the documents, you find a way to make a network out of them, and you can draw knowledge, information between from this kind of modeling. Again, this is not a network per se. This is not a network in the real world. This is a transformation of the data that we force into a network. And again, with this, we can find out a lot of different things. Think about communities. Find communities here. Will you find communities of people that have, I don't know, common interests, common, I don't know, enterprises, common, they work together, something like that, or in the same sector, something like that. So let me just check that there are no questions there. So I hope that I showed you some of the beauty of networks. What we will do now is we will go through this notebook that I prepared, which shows how to do network analysis with Network X. So this is more advanced than what you will see later, but since it's code, there is code involved, I want you to be like kind of fresh, okay, fresh minds. Okay, so later when you are more tired of hearing me talk and talk and talk, we will do more easy stuff, okay? But for now, we will do some coding. Again, you don't need to memorize the code, and most of the time, you don't really need to understand what it does. The most important thing is that you know that it exists, and then if you need it, you can look out for documentation. You can ask Gemini. So for those of you who don't know, this is called a Colab environment. Colab is a service offered by Google. Google Colab here. It's a service offered by Google where you can run Python code. Okay, so you basically, sorry, this is in Italian, but the idea is this: you have some code. For instance, here you have seconds in a day. You have 24 hours times 60 minutes times 60 seconds, and you get that in a day you have this 86,400 seconds. So this is this code that is running on Google's computers, and you can edit. If you know some Python, you can work with it, and so on and so forth. And there is this very powerful tool here. It's called Gemini, which is an AI, which I can ask, write code to blah, blah, blah. Okay, write code to do this. And it will do it. Okay, so most of the time it will be correct. So you just need to understand that, I would say, what kind of things you can do. And then if you don't really remember the line of code that you need to use, you can either look for documentation or you can also ask Gemini. That's it. Again, you don't need to follow along with me. There are no exercises that I'm leaving you for you to do. But again, just let's go through this code and analyze it. So the library that is most used to work with the networks is Network X, and is very simple to use. the idea is that there are some network objects, and you call some functions to analyze them. These functions are defined by network X. So the communities, the degree, the density, all the things that we have seen so far and more can be computed in network X. You just need to find the right command. So now, trust me, this is not really important. Now we are doing some preparatory stuff. Why it's not starting? It will start. It will start. So basically what this does, it imports the necessary library, the necessary packages that we will use. So if you open this, when you will be on your own and you will analyze, you will play with the networks, you will find links to the documentation of network X. If you don't find it, network X, you Google it, and here is a lot of documentation of all the things you can do. Okay, documentation here. A lot of the things you can do with networks. There is a tutorial reference with all the codes and tasks that you can do, bibliography. Everything is very well documented. There are a lot of tutorials, YouTube videos. So if you want to explore more, there is a lot of material. So the idea is that you have this kind of object here. So basically what we do is we import network X, import network X as an X, which means that we will, when we want to use some function that is that comes from network X, we'll say nx dot something, which means network X, help me do this. Okay. So we create this graph G. We store it in a variable. Okay. So we say, hey, network X, create a graph and store it in the variable G. Then I want to add an edge between node A and node B, but these nodes don't exist. So network X will add the nodes and then already add the edges. So we ask network X, add these 3 edges and then draw the network. So here we say add edge A to B, edge A to C, and edge B to C. Then we say draw the network with labels. We want to know which kind of things are, and the node, we specify the node color. And this is the network that we created. Okay, this is very ugly. I know Python is not very good at producing very good visualization. That's why we'll see another program later. But the idea here, let me check the time. Okay, the idea is that with very few lines of code, we created a graph, a network, and we inserted manually some edges. So in the worst case, if you don't know anything about coding and you have a small network, what you can do is you have in your mind or on a piece of paper all the edges, and you manually say, okay, add edge from Andrea to Beatrice. Okay, add an edge from Andrea, something like that. Okay, so this is the worst case scenario. But sometimes you already have data in a spreadsheet or on a TXT file or on a Word document somewhere. Okay, and there are a lot of network data sets that are available. And network X provides you a lot of ways to work with these graphs, with graph data. So here, what I forgot to show you is that you, with the same rationale, when you add an edge, you can also remove it afterwards. Remove a node, remove an edge. And then when you draw again the network, now you just have a disconnected two nodes with no edges together. So again, just to show you that this is the most basic commands. You can add an edge or remove an edge, add a node or remove a node. That's it. So when you are reading a graph from file, what you want it to be is basically an edge list. Most of the time you want a file that is formatted like this, okay? You have node A and node B. So this is an edge that goes from node A to node B, from node B to node C, and so on and so forth, okay? So it's a text file, and usually you find it as CSV or TXT, which is it's not really important, but basically you want this to be like this. If you're working with Excel data, Excel internally saves its data like this, okay? This is like the first cell at the top of Excel. This is the second, and then you would have a third, and so on and so forth, okay? But there is this kind of idea of elements separated in rows and columns, okay? This is a very small table. So for the rest of this example, we will work with the Facebook data. That this is a already collected data set, which is freely available. And I wrote the function to download it up here. So that's why I told you to trust me, download if needed. Okay, you don't need to understand why this works, how it works. There is some data from Facebook that we will be analyzing right now. So the file that we have here, that we have downloaded, is basically this file here, Facebook combine.txt.gz, and it has precisely this format here that I'm showing, this edge list. NetworkX provides a function to read the edge list, where I give it the path to the file. So my file is stored, let me show you, in data, Facebook combined, okay? So basically what I'm doing here is read edge list, data, blah, 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 Facebook combined, okay? So this is what I'm telling it to do. Creating using a graph, and we say that all the elements in these networks are numbers, integers. This is just because the data from Facebook is anonymized. We don't have the real name of the people. We just have some numbers that tell us this guy is number 7, number 144, something like that. So this is one of the most critical steps if you work with networks, because I understand that once you have your network loaded, you can analyze it however you want, also with Gemini. But the first obstacle is getting it to work, right? Getting it into a graph object of some kind. So the official documentation of NetworkX has a lot of methods to do this. If you have, I don't know, here, edge lists, JEX, which are another file, GML, GraphML, JSON. There are other formats, but also like you can find it here. You can find ways of reading, how to say, like spreadsheets. Okay, so here you can find ways to read and write graphs in NetworkX. A lot of different formats are supported. Most of the data you already have can be imported in NetworkX with one of these methods, maybe with minimal modifications. Are there questions so far? No questions. But if you have questions, of course, feel free to ask. So again, we read this and we print it. And when we print a graph, it will not display it, but it will say how many nodes and how many edges it will have. So what does it mean? This graph here, it has 4,000 nodes, 4,000 people on Facebook, and 88,000 edges, a lot of data. This is very large data that you will typically work with in Python, not with other simpler programs.
Andrea,
Yes.
there is a question regarding the Google Colab notebook. You have said you are
Yeah.
not sharing now, right? We are following you and you will share the notebook later, right?
Yes.
Mhm.
So let me just. So if you manage to go here to this link here that I also shared in the chat,
Okay.
it will open this. And there is the notebook here.
Okay.
What you need to do, so you basically click on this. It's not working. That's the problem. Okay, so it's not the notebook is not currently here. Yes, it's not showing, but I will upload this during the break. We will do a break in some time. 7:30. Okay, that will be great. So we will do a break and I will upload it, and so you will have it here. And then what you need to do is basically upload it into Google Colab. So basically you open Google Colab and you can have like, where is it? If I go on Colab, here, you can open a notebook. So sorry, this is in Italian, but there is this idea where you can open a notebook and upload it from your computer. Again, whatever you study here on Colab is not on your computer, it's on Google's computer. Google is providing you with space and power, computational power, which means all the data that you upload it temporarily to a Google server, which means, as some of you know, that if you stop and go make some coffee and then come back, sometimes you will not find your data anymore. It will still be on your computer, but not anymore on Google's computer, because Google will say, okay, this person is not using the Colab anymore. So let's free some resources and give them to someone else. Okay, so what we do here is we have a very large network. How do we visualize it? So Network X has functions to draw the nodes, to draw the edges separately. So these have a lot of parameters. So you can say the node size, the node color. There is a lot of, again, documentation on these parameters. You don't need to memorize them. But there is also this simpler way that I use here, just draw. Okay. The difference is that when you use draw nodes and draw edges, if you do this separately, you have more things you can change. What I'm doing with this code, you don't need to understand it. You just need to trust what it does. Is we filter the graph, because it's very, very large. Again, 4,000 nodes are very hard to visualize. A lot of dots, right? So what we do here is we take 1,000 nodes, or maybe let's do 500 nodes. And then we take 500 random nodes from this network and only plot those, only display these 500 nodes. Okay, so these are 500 dots. And you can see there is a community here at the center, some communities here. Again, these emerge naturally, right? These are people that are friends on Facebook. That's why the network that we're using is not directed, because friends on Facebook, if I'm friends with you, then you are friends with me. Okay, there is no direction. And again, this is a sample of 500 nodes from the Facebook network. If you want to change it and display like 100 nodes, it takes 100 nodes, and you see there is very few connections left. But again, the full network is much more connected than that. So when you have a graph object, you can work with it, work with the nodes and the edges to do something, okay? So what I'm doing here for each node in the graph nodes do something. I could say, I don't know, print the node, okay? Or I could do print, I don't know, the degree of the node. We will see how to do this in a bit. Again, with the edges is the same. For each edge in the edges, you can do something. All graph entities can be used to store some attributes, so like edge weights or node labels. So an interesting trend of research right now is trying to not only use networks with their structure, but also incorporate metadata, information about the nodes, about the edges, to draw more information from this network. And again, if you go to the tutorial of Network X, there is other ways in which you can add more information, like node attributes, edge attributes, and so on and so forth. Again, this is linked in the notebook that I will provide. If you want to, so we have already seen that if you print a graph, so if you do like print G, it will show you that you have a number of nodes, a number of edges, okay? If you want to use the number for some calculations, you have the number of nodes, number of edges. This thing, it tells me if the graph is directed. Is there a direction? In this case, it tells false. It's not directed. Okay, so all edges are symmetrical. And then I can look at degrees. Just checking the time. Let me see. Okay. Okay. So I've been told that there is a red line drawn on the screen. I'm not really sure how to remove it, but probably I will share my screen again and it will stop. Let's see. Can you see my screen? Yes, okay. There is still a line?
No.
Okay, that's great. That's great. Sorry about that. So the degree, again, the degree, let me just write it. Degree is number of connection of a node equals number of edges adjacent to the node. Okay. So when you have a graph, which we saved in this G, capital G variable, you say, so let's do like this. If you take G and you do G dot, then Colab will tell you a lot of things you can do with this G. Some of these things, they don't make sense to you right now, okay? Because you don't know what is a subgraph or a multigraph or something like that, okay? But if you go through this, you will find eventually maybe something that you might use. For instance, we already seen the degree, but here you will see a lot of other things: number of nodes, number of edges, remove, size. So if I have an undirected network, I can convert it to directed. Again, you can explore this or look at the documentation. But one thing you can do, as we were saying, is I have my graph and I want to look at the degree. So I say, first, let me show you. My nodes are like this. Okay, this is the list of my nodes. 0, 1, 2, 3, 4, 5. Okay. So my nodes are numbers. So let's say I'm interested in node 1 and I want to get its degree. I do G.degree of node 1. Okay. And here, if you go over the degree, it explains how it works. It explains what it wants. There is some example. Again, if you find yourself stuck, there is a lot of documentation to help you. So the degree of node 1 is 17, which means that node 1 is connected to 17 other people, has 17 friends on Facebook. The average degree, which is basically how many nodes is a node connected, sorry about this. How many nodes is a node connected on average? So in this sample of 4,000 users, we see that a node is connected to 43 friends on average. So if I pick a random node, on average, it will have 43 friends on Facebook. Only from the data that I am having, and this is not true for the whole Facebook, right? It's just the small sample that I have. Then you may want to look at the degree distribution. Again, here I'm showing you the degree of the nodes, the number of connection of a node, and the count, how many people have that specific degree. So you see what we have seen before, that a lot of nodes, most of the nodes, a very small degree, very few connection, and a lot and very few nodes that you cannot even see in the graph. You can't see these here, but there are people here. They're just too small to show up in the figure, that have 1,000 friends on Facebook. Okay, the popular guys. So mathematicians and statisticians, when they want to visualize these skewed distributions, which means where you have these very uneven distributions where some data will not show up, what they do is they, let's say they modify the x-axis and the y-axis, they apply a log-log transformation. If you don't know much about mathematics, don't need to stress about this. What it does is basically, now we don't have like here 0, 200, 400, 600, blah, blah, blah. We have 10 to the power of 0, which means 1. 10 to the power of 1, which means 10. 10 to the power of 2, which means 100. So now we can see that 10 to the power of 3, which means 1,000, there is at least one guy here that has 1,000 friends. And there are others that are close to having 1,000 friends. So this is just a way of showing very skewed distributions in a very compressed format. And here I'm showing you the count. So this is the number of nodes, the average degree, standard deviation. Again, if you don't know what standard deviation is, don't really need to worry about it. It's just an index of dispersion, how many, how much these degrees deviate from the mean. If that doesn't make sense to you, totally understandable. The idea is it is a measure that tells me something about how my nodes, how my values are distributed. Not really important right now, but pick up a statistics class if you don't know what that means. Minimum and maximum, and then these are percentiles, which again are just indexes of a distribution. Okay, so the 25th percent, if I order all my points, it will have degree 11, something like that. Just again, if this doesn't make sense to you, these are just common ways of common statistics to analyze curves or distributions. So what I'm showing here is we want to see how many nodes have a given degree. Okay, so I want to know how many nodes have a degree that is at least 100. And so it tells me that 12% of nodes have degree 100 or more. Let's see how many 1,000. So again, you change the parameter here, and only 0.02. If you go back to like 10, you see that most nodes have degree at least 10. Okay, this is a consequence of this distribution here. If you look at this here, you see that there are a lot of disconnected components, right? There is a bubble here. Maybe let's do it a bit with more nodes. And then we will stop in a few minutes. So there are some islands in my network, right? So this is a one big connected island. Okay, but this is a small island, this is a small island, this is an island, something like that. These islands in network science are called components of a network. Not really important, but the idea is you have some, these are not communities, these are really islands of like separate networks inside my whole network. And you can extract them with the network X. So, for instance, here you can see the neighbors of a node, of node 100. It has these neighbors here. You can look at its friends. So here I'm drawing node 100 in red, and all of its friends and the connections between its friends. And then I'm extracting the number of connected components that in the whole Facebook network is just two connected components. Paths, we have seen this before. So a path is basically the route that goes from one node to the other, right? So if I want to know, if I take this ego network here, the network that is built around node 100, and I say, okay, how many steps does it take to go from node 163 to node 323? Again, from this node to this other node, it tells me, okay, you start from node 163, then you go to node 0, then you go to node 323, something like that. So you have this, this is the shortest path between the two nodes. If you care about the distance, you care about the shortest path length. So only 2 hops, right? So if I see, let's see, what were my nodes? 63 and 323. 163 is here, and 323 is here, okay? If I want to go from here to here, well, you see there are multiple paths, but one of the paths is go from here to here, and then from here to here. So you have 2 hops, 1 and 2. Let's see. Okay, the rest of the things in Python are very straightforward, I would say. So we can do some break right now. Is it 7:30 on your end? Yes, it should be. Yes. So I would say let's do some like 10-minute break, or if it's fine for you, let's say 10 minutes. If you need more, just tell me. And then we will do the rest of things you can do in Python, and then move to, let me show you very briefly, this Gephi here. Gephi is a network visualization tool that this does not require any code. You just input your network and then push buttons, which we really love, right? No code, no need to ask Gemini, just push the button and it will do it for you. And you will not be able to, yes?
How about given break for 20 minutes?
Perfect, no problem. Okay.
Then we can
So
have short breaks later on, but the first one should be a bit longer, I think.
yes, it would be great. For me, it's not a problem to have 20-minute break. Okay, so let's have a 20-minute break. We will see each other at 7:50, right?
Yes.
Okay, so I have uploaded the materials to the website. Again, there is a link in the chat if you need it. If you need me to paste it again, it's this here. So you have this tinyurl.com/yadesa-net. Okay. So this brings you to this very small website. The idea is there are just links to the materials that I'm using, and also some suggestions for further readings. If you use the notebook, if you use the notebook, if you don't see this, this writing here, notebook, blah blah blah, you just need to refresh your page, and it will work if you don't see it yet. Again, you don't need to download it and to follow along, but if you want to do it, you feel free to do that. The important thing is that you make a copy and you work on your copy. I'm sharing with you a link to the notebook, but then you have to go to File, and then there will be something like Save a Copy on Drive, Make a Copy, something like that. Otherwise, if you edit it and then come back later, you will not save your changes. So everything you did will be lost. So again, if you need it, just make File, like to click on File, then Make a Copy or something like that. Otherwise, everything will be lost. In the website, you see some repositories of network data. If you want to play a bit, if you need it for some student project, something like that. In particular, there is this network repository here that has a ton of networks. And this is useful also to understand the power of network science, animal social network, brain networks, collaboration networks, citation, ecology, economics, emails, and so on and so forth. You see, there are plenty of applications of networks. Did I share my screen? Yes, I think I should be. Yes, I'm sharing my screen. So again, there are a lot of networks. You just basically, you go into your family of networks, and here are a lot of networks that you can download with some statistics. So this is the number of nodes, the number of edges, and some other statistics that maybe do not make really much sense to you right now, but they are explained in the website as well. If you click, there are some explanations here, and there is also a visualization on this website. Else, another thing I forgot to mention. So this book here, Atlas for the Aspiring Network Scientist, is 100% free, which means you go on the web. You can buy it if you want, but I'm not affiliated with the guy. He is Italian, but I don't know him personally. You can download it for free. I don't want to start download now. But again, you can download it for free, and it is a very large book. It's hundreds of pages, but it is explained in a very easy tone, which means there is some mathematics, but it feels like this guy is talking to you at a bar. Okay, so everything is like, the examples are really simple. The infographics are very well done and very easy to understand. There's lots of explanations. There's exercises if you want. But again, this is very, the focus of this book is not to cover everything of network science. It's to cover it in a super, super, super simple way. If you're looking for a formal book, like a good textbook with proper technical stuff, this is not the book for you, but this is the easy one that anyone can pick up at any time and learn a lot about network science. And again, it is free, which is great. And then these instead you have to buy if you want, but I recommend them. I read these, and these really showcase the powers of networks. So in particular, this one it is from 2002, but is very good read. So let's go back to Python. Go back to Python, maybe here. I think I have to execute some cells again. Yes. Let's for sure. So what we have seen so far is, again, I'm throwing a lot of things at you. I know that it can be hard to keep everything in mind, and you don't really need to. I'm just showcasing you some things, and what I want you to think is, how can I apply this to my own research? So you are a political scientist, and you can study how people from the parliament interact, okay? Or there are a lot of studies that do, for instance, people who vote on the same thing, on the same bill in the parliament in the same way are connected together, okay? So these kind of networks tell you something about co-sponsorships, right? Some people who agree on some matters. I made the example before of trade networks between countries. So again, this is I'm sure this is a very diverse class. Like, a lot of people have different backgrounds, are doing different research, but try to focus and try to think, okay, this is cool, but how can I take this number, take this function, this idea, how does it apply to my own research? If there is time later and you want to discuss here, for the benefit of everyone, we can do this as well. Are there questions so far, or can we go on with the... I think we can go on, but if there are questions, you just ask them. Okay. Very quickly, degree, number of connection, neighbors, number of, again, it is another way, the neighbors is the set of people that I am connected to. So the paths are the routes I can take, the hops I can make in my network. There are other things. The diameter is the longest, shortest path, which means, bear with me, the diameter is if you take the two farthest people, the two most distant people in the network, the shortest path between them will be the diameter of the network. The diameter is basically how distant are the two most distant elements in my graph. Have you heard of 6 degrees of separation? There is movies about it. There are books that tell you about 6 degrees of separation. What does it mean? Well, the idea of 6 degrees of separation comes from network science and comes exactly from one of the guys that I cited you here, this Barabasi here. He's one of the most important people in network science. Basically, there are some mathematical rules that tell you that since a lot of networks behave in the same way, we can estimate, even if we don't have the full network of all the people in the world, that if you take yourself and any other people in the world, Donald Trump, Taylor Swift, the president of China, I don't know, whatever, yourself and anyone else in the world, some random people on some random island in the world, there will be at most 6 handshakes between you and them. So you shake your hand with your cousin who knows someone in the US, and this guy in the US works for someone who knows Donald Trump, for instance. Okay, it's something like that. So even if there are 8 billion, is it 8? Well, billions of people in the world, on average, you have this kind of distance of 6, 7, sometimes it depends on who you ask. But this thing is the kind of thing that network science tells us about human behavior and how societies are built. Okay, so if there is a way, if you want to get to someone, there is always a way, and it's just a few steps away. Okay, so real world networks have very short paths, short distances, and this applies again to a lot of networks, also beyond human social networks. So here I'm showing you some other indices that you can compute. Again, it is not important that you memorize them, just try to look at this and try to think how does this apply to me? How does this apply to my network? The network that I could study if tomorrow I decided to become a network scientist or to apply network in my social science, in my psychology, and whatever. So density, we've seen this before, is the fraction of edges that exist over all the possible edges. So how many edges exist over all the edges that I have in my network? And in this case, it's very small, it's 1%. So if I have 4,000 nodes, and 80,000 edges, which is our case, that is only 1% of all the possible nodes the only possible edges that I could have. This is true for most networks. Most networks are sparse, which means not dense, which means that most connections are, I would say, essential. Okay, you don't have all the nodes connected to all other nodes. You have just a few connections, but these connections somehow allow you, for instance, to have only 6 hops, 6 handshakes between you and anyone else, right? The human social network, the social network of all of humanity, is very, 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 I mean, it's not dense at all. It would be like 0.00000 blah, blah, blah of density, and yet you would have only 6 people between you and anyone else, 6 or 5 or 7. Triangles. So there is a property in social science that's called triadic closure. The idea that humans, but again, not only humans, also animals, and also any other network, there is this idea that we tend to close triangles. What does it mean? If you go back here, let's remove this. So you see that we have an edge from B to A and an edge from A to B to C. Okay, so A knows B and C. What will happen? It could happen, it is very likely that since A knows B and A knows C, that it will introduce B to C. I don't know if this makes sense, right? What happens is, since A knows both of them, humanity has this tendency of closing triangles, okay? If I like you and I like someone else, and then you are probably similar to me, that other person is similar to me, so the two of you are similar as well. So I could introduce you. This is how most love relationships are formed. Well, nowadays people meet online on, like, this kind of dating apps. So it's not really true anymore. But back in the day, how to say, but traditionally people meet when they are introduced by someone else. This idea that you close the triangles. So you might be interested in counting triangles. So here what I'm doing is I'm counting the triangles in my network, and I'm just looking at the node 0. Or maybe we can do node 100. Just to see how many triangles is my node included in. I would just skip clustering and average clustering just because it's not that hard, but I don't want to overwhelm you with very specific statistics. But basically, it's the fraction of possible triangles. It's a local measure of density. So the idea is that you would have local clustering that is high, but the global density that is low, something like that. So what I told you before about homophily, this idea that similarity breeds connection, the effect of this is that a lot of people with the same characteristics are connected, right? More than random effect. This translates to a lot of characteristics, statistics. Not only demographics, not only some ideas, beliefs, religion, politics, but also some other characteristics. Think about what we learned with the Epstein files. We learned that all the rich people are connected, which means there is some connection not only in demographics, not necessarily in demographics, though you could say that all of these people are rich white men, but not only that, but there is also assortativity, or this kind of idea that similar people are connected in wealth, okay, social class. In networks, this is translated with degree assortativity, for instance. So you could say, I'm going to explain what this means in a bit. You could say that degree assortativity means, are nodes with the same degree connected to each other? So are high degree nodes connected to high degree nodes, or low degree nodes connected to low degree nodes, something like this? So most networks are disassortative in degree. What does it mean? It means that high nodes are mostly connected, highly connected nodes are mostly connected to not very well connected nodes. Real example, influencer on social media, very well connected, but most of their connections are normal people. And that makes sense, right? You have a very popular person, but the follower of this person are random people, normal people, me and you, right? So it is not true that popular people connect only with popular people. They connect also with common people, random people. So this is awful. But yeah, this idea here, there is this disassortativity, you would say, in degree. But what we were saying before, if you look at other characteristics, then there is assortativity. This homophily produces assortativity. Assortativity is this idea that nodes with the same characteristics are connected. Very briefly, I'm showing you this network. This is a very popular network example. These are friendship relationship at a karate club. You know karate, the sport where they hit each other. I don't know how to describe karate. Yeah, I know. So there were these two clubs. It was originally one karate club where they all learned karate together. But then these two guys, Mr. High and the officer, they argued and they split. Okay, And so some people ended up following Officer, and some people ended up working with Mr. High. And so now what you see here is that the friendship relationship are mostly within the class, right? The people who follow one or the other instructor, right? So the orange nodes, the salmon nodes, are people who ended up with the officer, and you see that most of their connection are with other people that follow the same guy, and the same holds for the people who follow Mr. High. How can we compute this? There is a function, attribute associativity coefficient. If you are familiar with statistics, this is just a fancy way of calling a Pearson correlation. Okay, if you know what a Pearson correlation is, this is a Pearson correlation run on the edges, the attributes of the nodes. What we do here is we take the karate club graph, okay, we say the attribute club, and we compute this assortativity coefficient. The assortativity coefficient is positive and high for high assortativity, or it is negative if there is disassortativity. So if I had that most people connected with people from the other class, I would have a negative number. But now I have a positive one, and it's very high. It's close to 1, close to 100%. This is another way of looking at it. I'm counting the fraction of edges that go from people that follow Mr. High to people who follow Mr. High. So within the same class, 44%. Within the other class, 41%. And then only 7% are cross-class edges. I hope that makes sense. The idea is we have an attribute. In our case, is the club, but think about real networks. It could be gender, okay? Could be gender, and you could have like male and female people, right? Men and women. You would have, if this network was a network of male and female people, you would have, in this case, with this exact label distribution, you would have 44 edges, 44% of edges are connect only, male people, 41% connect only women, and 7% connect men to women. So this is just an idea. You have your network, you have some labels on this network, on these nodes, and you compute this statistic that tells me how are my edges arranged. Communities is a very hot topic in network science, particularly because there is no fixed way of defining what a community is. So we said before that a community is a set of tightly connected group of nodes. So you have a group of nodes that is very well connected with themselves with respect to the rest of the network. But how do we compute this? Well, there are a lot of algorithms, and we will not see them. We'll just use one here, but you don't need to understand how it works. It optimizes for a function that is called modularity, that is a proxy of how well connected are my communities internally, and how badly connected are my communities externally. Again, if that doesn't make sense, just trust that modularity tells me how modular my network is, how broken into communities my network is. And what we do here is we compute this, we use this algorithm, greedy modularity, which optimizes for modularity. And then we look at how many communities we found, and the modularity score and the sizes of the communities. Now it takes a bit to run because it's very expensive as an algorithm. What does it mean? What's happening here? So we found 13 communities in this Facebook network. So 13 different groups that are very well connected. And the graph has a modularity, with this partition, has a modularity of 0.7, which is very close to 1. These kind of indices always go from 0 to 1 or from -1 to 1. In this case, it goes from -1 to 1 to +1. -1, it means that it's not very modular. +1, it means that it's very, very modular. And in our case, it's very, very modular, okay? And it makes sense. If you think about people, these are people on Facebook. I forgot to mention. These are the people on Facebook. You have very well separated communities, right? If you take all the people from Ibn Haldun University, they will have a lot of connections together, but their Facebook friends will be very different. You know, you have your parents on Facebook probably, or your relatives, but your colleague will not have your relatives likely will not have your relatives on Facebook. So you would have these kind of separated communities. And this is basically the size of the communities. Community rank is just an index. It basically tells me it's just my 13 communities, right? So this is community 0, community 1, 2, 3. You remember, computer scientists like to start counting from 0. Ah, no, sorry, this comes from 1. My bad. Sorry, I just used to count from 0. So this is just one of many algorithms for community detection. We developed a Python library, in case of you're interested. We developed a Python library on community detection. There are a lot of methods. I would say, like in my opinion, you are fine by just knowing the most popular one. But, you know, if you care about communities that form based on how information is diffused, communities that form based on the spread of some properties, communities that form based on the temporal evolution of a network, then you might want to look at other algorithms that you don't need to learn how to implement, because they are already implemented in the community detection library, which is Python. And it's very easy to use, and there is a lot of documentation here as well. So this idea here is there are a lot of algorithms, and I compute whatever I want on them. So I apply them to whatever kind of network and extract these communities. And then what you would typically do is look at the people inside of these communities and try to analyze them. If you are in the social science, up until, I would say, 5 or 7 years ago, a perfectly publishable paper would have been take a graph, compute communities, analyze the communities. Nowadays, it's not that novel anymore, but there were a lot of people that were just doing that and publishing in Q1 journals. So again, this is a perk, I would say, of the interdisciplinarity, because you can draw a lot of knowledge by applying these standard tools to a lot of domains. And finally, okay, there are a lot of other tasks that you can do on networks that I'm not showing you because I know that this is already very overwhelming. For instance, there is a task called link prediction. So given a network, you are trying to predict what are the next links that will be created. This applies to a lot of different contexts. Friendship networks, this is what Facebook does when it tells you, there is this, or Instagram, if you use Instagram, it tells you, there is this person you might know. It uses network science and also NLP, text analysis. It uses a lot of things to estimate which are the people you might want to connect next. Also in social media, you scroll through some content, right? If you go on social media, you see some posts. This is another kind of network. A network, it's a particular network of users and content. So two types of nodes. And link prediction there tells you which kind of content this person would like to see. Okay, so these kind of evil algorithms that are, feeding you things you like, and that we always talk bad things about these kind of algorithms, right? Now you know how they work. They work with network science. They work with a very simple approach that tries to estimate if there will be a link between you and this kind of content specifically. Of course, I'm simplifying stuff. It's very much more complex than that. And we don't really know how this algorithm works because the companies own them and they will not tell us how they work. But it's very, very likely that they work in a link prediction, right? Another thing that we will not see is dynamic networks. So networks change in time. Your friendship network is not the same as it used to be 10 years ago. And there are other advanced stuff you can do with temporal networks, networks that change in time. Another thing we will not see, is diffusion on network. So how we have seen paths, but how do properties spread through the network? Think about fake news, think about viruses, think about goods on a supply chain network. A lot of things spread through the network, and there are some models that tells you what happens if my network has these characteristics, this degree distribution, this density, blah, blah, blah. How will the property or the agent, the pathogen, whatever properties you're studying, how will it spread? Which nodes will it infect? And so on and so forth. So this is some ways of forecasting. Again, this is just very complex stuff that is, I figured it would be too much to fit into this class. Keep in mind that at the University of Pisa, we do a 60 hours course on this, on network science, on social network analysis. And this is like a very, 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 very condensed class based on that course. Okay, so again, there is a lot to cover in network science, and now we are just, I'm throwing some things at you in the hope that you can find something that is useful for your field. One thing I really like about networks is that, again, they tell us a lot about things, human behavior. I work with social networks, so most of my examples are with social networks, with human social networks. But what I really like is that there are some mathematical rules that explain a lot of things, right? And you can see on the screen this thing, it's called the friendship paradox. So I don't know if you've ever felt that your friends are more popular than you. Well, that is because it is true. This is not bad news. This is precisely normal. If you feel like your friends, like when you went to high school or in general, if you feel like some people are, like, your friends are always more popular than you, this is true, and it's true for a mathematical properties of network. Precisely the degree distribution that we've seen before. I will not go into the detail, but if you look at the average degree of a person in this Facebook graph, you have 43. So on average, one person is connected to 43 people. But their friend, on average, is connected to 105 people, more than double. And this holds true for almost 90% of the nodes. Let's throw away the numbers for a second. Let's think about what that means. Since we have few nodes with a lot of connections, these few nodes with a lot of connections will influence how all the other people are connected. What this implies is I am connected to some people, but somehow in my set of connection, there will be some people who are very, very well connected. What this means is that on average, mathematically, this is a mathematical rule. It's something that happens, if not all the time, most of the time. Your friends are more popular than you are. And this is, again, not your impression. This is true. And this is not, again, it's not meant to be a bad thing. It's just how we, if you look at your friends, you are very, very likely to find that they are more popular than you. So just deal with it, okay? It's not something that depends on you. It's something that depends on how humans create links, on how society is structured. So if you felt like you were not very good at making friends, now you have your answer. Maybe it's not your fault. Maybe it's just a fault of a complex system that is humanity. So this covers everything that I wanted to show you in Python. I hope you're not crazy tired. I swear that the rest of this class will be easier. I'm checking the time. The rest of this class will be way easier because we will not have to look at the code. I mean, if you followed my instructions, you didn't care about the code anyway right here. But in case you are stressing about understanding what every line means, in a few seconds, you'll see Gephi, which is this tool we will use to analyze networks and draw some insights. So again, in Python, you can do very complex stuff. For instance, link prediction, community detection. You know, there is a lot of people that develop software to do advanced processing of very large networks. Battery is low. Okay. So if I'm going to show you something in a bit. If you want to do something with a network and you cannot do it in Gephi, the software that we will see in just a bit, you will probably be able to do. You will for sure be able to do that in Python. So the way I would do it, if I would, how to say, if you're not very comfortable with Python, let me turn the light on. If you're not very comfortable with Python, what you might want to do is just use Gephi and then only come to Python when things, when you want to do something that Gephi does not allow you to do. Okay, if there is some, I don't know, you've seen a measure today that is not within Gephi, then you can go in Python and try to find a way to do it. Remember, always, there is, if you work on Colab, there is Gemini here to help you. And right now it is free. So it would be a good idea to exploit this. Are there questions so far? I hope I didn't lose most of you. I hope that some of you are still with me. Please bear with me. Just 1 hour more, and then you will not see me for a very long time. So, okay, again, Python. We've covered the basics. NetworkX. Maybe what we can do very briefly is, before going to just to have a complete picture. Here you can see everything you need in NetworkX. How to create a graph, the algorithms that you can apply, how to draw it. If you're interested about efficient processing and data structures, probably not, but you know, what kind of of graphs there are, directed, undirected. Before we briefly seen that network X has multi-graphs. What do they mean? I don't know. You can find information here. Algorithm for assortativity, bipartite. Bipartite is what I told you before. When you have nodes of two different categories, you have humans and content on social media. Centrality, we have not seen centrality measures, but you can find them here. And again, communities, components, a lot of other things. Most of these you will not need them, but here there is link prediction. So again, if you want to do something, you can probably do it here, and you can find the way to do it by browsing this documentation. And if you are too lazy to look at documentation, Gemini has already trained on this documentation, so they know it very well. Okay, so what we will do next is I'm going to show you Gephi. I've talked about Gephi before. Gephi is an open source software. Open source means that the code used to build Gephi is public, which means anyone with sufficient skills in computer science can look at the code and modify it. We will not do it, but this means this is perfectly safe. What does it mean? It's safe to install, it's safe to work with, because a lot of people have looked at the code and they have confirmed that it is not malicious. Okay, so I will not let you install something on your computers that might contain a virus. We know for sure that since we can see all the code, we know for sure that this is how it is built. For instance, if you use Microsoft Word or Excel or something like that, those are not open source programs, okay? So we don't know how they work, if they send some data to Microsoft and so on and so forth. But Gephi, it stays on your machine. It will not send data anywhere unless you allow it to do it, and so on and so forth. So it is a very perfectly safe environment to work with. You can install it on a Mac, on Windows, on Linux, on every kind of machine you want. There is only one problem with Gephi. Gephi sometimes stops working. I don't know why. A lot of students have this problem. A lot of people who use it have this problem. Gephi has been around for a lot of years, more than 10 years, and they haven't fixed the problem. But sometimes you work with it, you do something, and it stops working. I don't know what to tell you, but this is simply how it is. But it's also very fast. So if it stops working, you can just open it again and upload the data again, blah, 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 and you can get to the same point in just a few seconds. So recently they launched this Gephi Lite, which is an even simpler way of using Gephi, which even less capabilities. But if you want to do some quick demonstration, here, for instance, there is a graph of Les Miserables. This is I don't know if you know Les Miserables by Victor Hugo. Very, very nice. Look into it if you can. Basically, these are people who appear in the same scene in this Les Miserables play. Okay, so this French play. These nodes are connected based on whether they appeared on the same scene, and the dimension of these nodes is based on some kind of probably on the degree, something like that. Okay, so very briefly, this is what you can build with a very simple tool, and this does not require code. What we will use today, however, is not this online version, which doesn't have many things. We will use the desktop version, which means it's a program you install on your computer. Here, we will use this one. You don't need to install it. Sometimes it takes a bit of time to install it. There is a lot of documentation here. If you go FAQ, frequently asked questions, a blog, GitHub with the code, quick start to install it very easily, import. Again, if you get lost and tomorrow you want to work with Gephi, a lot of documentation. Computer scientists don't like to document stuff, but everyone does it. So if you want to be a computer scientist, you have to document stuff. So everything that a computer scientist has ever written, it is documented, even if they don't like to do it. Okay, so you can trust that most of the code that you will see, that the software that you see is documented somewhere. Okay, so I have already installed Gephi, and I'm going to open it now. Okay, where will it open? Which screen? Okay, so this is a Gephi screen. It can be overwhelming. You see a lot of things on the screen right now. Don't look anywhere. Look at this very big blank screen. Everything else will be explained later. Okay, so here is where our graph will be. The first thing we need to do is import our graph, right? And we have seen that there are a lot of ways in which you can have a graph. You can have an edge list. There are different formats, right? And so Gephi supports some of them, but not all of them. But it supports the edge list. So this idea that I have, a list of edges. So one row for one edge, right? So like a spreadsheet, okay? What you would do is you would go on File at the top, and you would have import spreadsheet, import database, import something. There is a way here to import your data, okay? I will open a recent network that I worked with, just to show you some of the things you can do, okay? If you are interested in importing data in different formats, there is documentation on the Gephi website. We will import this network that has 36 nodes and 62 edges. It is not dynamic, it's not temporal graph, right? It's not a multi-graph. We don't know what that is, we don't care. And basically, I'm loading this file. It is in GEXF format. It is a format that encodes a lot. It is a graph format, okay? It's just very, very used in network science. And what you can do if you go in Python, where is it? In Python, you could do network X dot write JEXF with your file. So you put the graph and it saves. And then I'm missing something. I'm missing the file name, graph.jexf, something like that, right? And I will have my graph saved here. So this is just a format that I use to save my graphs. I import the graph, and this is what we see here. So this is not really different from what we have seen in Python, right? It's very ugly. So what can we do to make it better? So there are a lot of tabs. You see there is a tab here, measures here. And if you have installed Gephi, your Gephi might look a bit different than what I use. Don't worry about it. Everything is somewhere in Gephi, and there is documentation to help you. Very well written. So what we can do is, what I like to start from is try to get a picture of my graph, how it is arranged. Then I will tell you what this graph is. So at the bottom, there is this thing here, layout. It's called layout. Choose a layout. So a layout, basically, there are some algorithms that arrange the nodes in a certain way to make pretty pictures. That's it. It does not tell me anything about the graph. It just moves the node around in a way that the algorithm thinks it will be pretty. Okay, the one I use is this Force Atlas 2, which is, again, you don't need to understand how it works. You just need to push run here, and it will, again, arrange the nodes in a certain way. And then you stop it, and that's it. So this is already better, right? So what is this network? This network comes from a sawmill, a mill where they, how to say, they cut wood, I think. So it is a factory where they cut wood, right? The people in this, the CEO of this company wanted to change something in how basically he wanted to reduce the rights of the workers. Okay, he wanted to do very bad stuff, and he hired a network scientist to do that. So I do not endorse any of that, but I'm going to show you some of the things you can do to accomplish a specific task just by looking at the networks and using the statistics that we have seen so far. Okay, this is just an example. Of course, I do not endorse reducing worker rights and using data science to do it. Okay, so the tab here at the top, it is used to change the appearance of nodes and edges. Okay, but before we do it, the tab on the right has the statistics that we have seen before. If you want to compute a statistic like the average degree, how many connections my every node has, I click run, and I see here I see 3.4, which means each node is connected on average to 3.4 nodes. And this is the degree distribution. Very ugly figure, but again, you see that there is, again, most of the nodes that have very low degree, and then some nodes that have a high degree, 13 degree, okay? But just one node has degree 13. If you have edge weights, which means if you have a lot of connection between the same two people, you can compute this other thing here. Diameter is, again, the distance between the two most distant nodes in the network. And Gephi explains it to you. Average graph distance, blah, blah, blah. It will explain everything you need to do. And this algorithm also computes some centrality measures. You don't need to learn what they do at the moment, but if you're curious, this is the explanation. It is explained in the... Gephi always likes to explain things to you. So you will find explanations of the things that it extracts. Let's ignore this for a second, but what we have discovered here is that the diameter is 8. Okay, so there are at most 8 connections between every node, every couple of nodes in the graph. Okay, the density, compute the density, we know this measure, not very dense, right? We have a lot of edges that do not exist. This edge from this to this does not exist. Notice what happens if I click one node, I can drag it and move it around, right? And if I hover over one node, I see all of its neighbors. This here, right? So it is good for a visual inspection of your graph. Of course, if you have 100,000 nodes, you cannot upload it in Gephi. Your computer will crash. So if for that case, you will use Python. But I figure that in most cases, networks in social science are small, unless, like, small, it means like less than 10,000 nodes. So if it's less than 10,000 nodes, you can work it in Gephi, I think. If it's less than 1,000, even better. Hits and page rank, we don't care about this. These are other centrality measures. Community detection. Here we have only two algorithms. Modularity is the same that we have seen before. And it computes the communities. It tells me the modularity and the number of communities. It finds 4 communities and it tells me its sizes, okay? This one at size 11, this one at size 9, and so on and so forth. And it tells me also the algorithm, the reference of the algorithm, in case you are interested in how the algorithm works. You can find reference, or you can cite it in your own paper. So yeah, you run this algorithm. Now we are computing these things, and then we will use them to color the nodes differently, to change the appearance of our network, so that we make pretty pictures and understand visually what's going on with the network. And that's it. I think this is not important because this is a dynamic network. Clustering coefficient, we can compute it. Again, you don't need to remember what clustering coefficient is, but again, these are some of the statistics that you can extract from the network. So now that we have computed our statistics, what we can do is change the appearance of our graph. Change the color with this button here, change the size, or add some text, okay? So if you look at nodes, we can partition the nodes, so which means assign a color to the nodes based on some community, right? So we computed the modularity and we used the algorithm to partition our network. And so now my nodes have this modularity class. So now I see here that my 4 communities, 0, 2, 1, 3, have been assigned different colors. I can apply this here. And now you see visually, we have 4 communities with 4 different colors. So now you see why visualization can be misleading and communities can be not really well defined. Look at this node here. This node here, it tells me it is in this community, but visually I see it closer to this one for some reason, right? So if you look, the larger your network is, the less you have to care about these wrong assignments. Also because there is not really a right or wrong assignment. This is just an heuristic. What does it mean? It means that different algorithms will return different partitions. If I run statistical inference here, it will only find, I know how the algorithm works, it will only find one community. Let's do it just to show it. Because of the property of this graph, if I color the nodes based on inferred class, which means the communities that it found, it only found one community. Okay, so different algorithms return different partitions. And also the same algorithms run multiple times. Some algorithms can return slightly different partitions. We don't care most of the time because these partitions make sense somehow. Let me just check the time. Okay. These partitions make some sense. This node, it only looks close to this community because of how it is positioned in space, right? This is why visualization are misleading, because I can drag this here. And now, like visually, you wouldn't be able to understand that this node is ambiguous, right? So I don't like to blindly trust the visualization of the network. It can tell me something, but always look at numbers to check that the figure is not lying to you. This applies to everything you do with data. I'm sure that you are aware of this. So another thing you can do is rank the nodes based on some centrality measure. So we have seen degree. Change the size of the nodes. So I click on the size here. I click on ranking and rank the nodes based on degree. I apply this, and so now it is very ugly, but basically now the nodes are larger, the larger it is their degree. If I want to make them larger, instead of making min size and max size, from 1 to 10, I put from 10 to 40. I apply, and now I have larger nodes. If your things overlap, there is let's go back to the layout. A layout has a no overlap algorithm, right? Simple. So now it is better laid out. So now we see that already that there is this person here, that it is very well connected to most of the people, right? To a lot of people, a very high degree. But we could use another measure like closeness centrality. Again, when you use centralities, it may not make sense to you, but you need to ask, what does this centrality tells me? This centrality tells me how distant my node is from all other nodes. And you see that most nodes now are larger than before, because nodes are all close to each other somehow in this network, because they all work in the same building, right? If I look at the degree instead, degree tells me something else. It tells me that it is clear that there is someone with disproportionate high degree with respect to the others. So again, there are different centrality measures, and different centrality measures will tell me different things about how the network is structured. There are guides, and also ChatGPT and Gemini and Claude, blah, blah, blah. They are very good at explaining centrality, differences between centralities. You could ask, I have these networks where nodes are countries and edges are peace treaties. What does degree centrality tell me? What does closeness centrality tell me? Blah, blah, blah. And it will explain to you very well how these tools can be used in your own research. Let's go forward. You can also add labels to the nodes. You can manually type. If you know that this guy, the name of this guy, you can type it. But in my data, there is already information on the name of the nodes, and I can pick it up right down here, somewhere down here. I think it's this one, text. What did I do? So sometimes Gephi behaves in unexpected ways. Okay, so you can see some words like mill manager here, right? Kiln operator. I don't know what a kiln is. I'm assuming it is like a machine. So here you change the font because this is very ugly. Let's do italic and Verdana, and the size, we put it down to 12. Much better. Not the best, but still way better. So let's look at this network. Now that we have some labels, we see that the communities that the algorithm found, even if we were kind of skeptical of these communities, we see that the nodes within each communities have some label in common. Again, this label was already in the data. I did not put these labels here. This HP here does not depend on the community. HP is basically the sector where these people were working. Okay, so there is this mill, this factory, and HM basically is one of the rooms. Okay, HP is another of the another room. So basically, this is HM1 is the guy who works in the room HM. It is like an acronym for something. I don't remember the acronym, right? But we see that our algorithm managed by itself, not using these labels, managed to recover automatically the communities based on the structure. For me, this is kind of a magic, right? Our algorithm does not know that these people are in the same community in the real world. We just input the network and say, okay, do your magic. And the algorithm found this community full of people from this HM sector. The violet community from HP. The orange community contains important people like mill manager, the owner, the forester, kiln operator, and some other people here from EP, and also Y. So again, I did not tell the algorithm that these people had the same worked in the same sector. The algorithm understood it by itself. So by the same logic, it can recover real-world information on your own data as well. Of course, you need manual inspection. You cannot trust it blindly, but most of the time it will work. So, yes. So now we have labels. We have what you can do is also work with edges. You can rank the edges based on weight, but I don't think that there is any weight on the edges. Let's change the size of the, what was it? I wanted to change the size of the edges based on the weight, but it will not let me do it. Then let's change the color based on the weight. But yeah, all edges have the same weight here. So you cannot do this. So something I did not show you before is this tab here, Data Laboratory. What is it? Basically, it is a spreadsheet with all the information I have computed so far. So it contains my edges, my nodes with ID and label. And then it contains a lot of information, the degree, the eccentricity, closeness centrality, some statistics that the class, some number of triangles, the things that I have found out with Gephi, the things that I clicked on, right? Yes, so this is it. This is, you can export this. This is basically the node table with all information about the node. There is an edge table that tells me there is an edge from HP1 to HP2. It is undirected. It has this ID, and weight is always 1 in all of this. Okay, so you can export it, and if you are more proficient with Excel, with other things, you can also analyze these things in with the spreadsheets. You can also like edit, right? You can change this and modify, add something, right? This is a data laboratory. You can edit your network if you need it. If you have to add links. So yeah, and finally, so these are the main tabs. The first one where you have change the appearance, change the layout, compute the statistics. There is also a hidden tab here, filter, where you can filter out some things. For instance, I want to filter only, I don't know, nodes that have a certain degree, only nodes that have a certain degree range, something like that. There are filters there. Just checking the time. And you basically you click on the filter, you apply it, and it will like not show the things that you filter out, of course. Then there is this, and that's it. This is basically most of Gephi. I'm not showing you this other thing here, center on graph, reset color. These are basically other visualization tools you can click on here to say if you want to select more nodes. Again, there are different things, but a lot of these things are very well documented. And then there is this final tab, which is called the preview tab. Don't ask me why it works like this, but basically this is another way of doing a visualization. So yeah, we already had this visualization tab here in overview, where you computed the statistic and blah, blah, blah. But for some reason, Gephi also allows you to have this preview here. And you will have preview settings, and you will have some presets that are already basically some basic visualization. Let's do default curved. We do apply, and of course it's very ugly. But then you have here, like let's say we will not show the labels. We click here on don't show the labels, apply. So this is way nicer than what we had before. Now you see these rounded edges that are cool. Again, this overview is used to compute things and inspect the graph. This is maybe easier once you have computed the things to plot a network, and then you can just like download it somewhere, right? Change the background. I want the background to be, I don't know, a very ugly color like this. Now let's do black. And you change it like this, right? And then you can export it and do whatever. And that's mostly it. Like this is most of Gephi, what it allows you to do. I will show you one last thing, but I don't think it's very like this only covers edge cases. So let's say you really like Gephi and you're curious about what else it can do. People are developing tools to sorry, my earphones. Can you still hear me?
Yes.
Great, that's great. People have been developing tools called plugins for Gephi that you can install. So we will not go through all of these, but for instance, if you know what JSON is, you can export in JSON. I don't know. Generate different kind of graphs, convert Excel and CSV files. This could be useful. I don't know how this works, but there is a homepage, so it is documented somewhere. Other layouts, if you want to, Geo layout, for instance, if you work with maps, you can map your nodes onto a map. Sorry, I said it bad. You can arrange your nodes based on latitude and longitude, for instance. Other centrality measures, a lot of other things, other tools, word cloud. If your network is based on words that co-occur in the same text and so on and so forth. Then there is a lot of things to find here. Some of the things that I installed that I want to show you is a similarity computer. Bear with me, what does it mean? If you have some information about, like you have a table, okay? Let's say that your table represents countries, and you have a country and GDP, okay? You can build a graph with this plugin where networks are connected if they have similar GDP. So I don't know why you might want to do that, but in case you want to do that, there is a way of doing it. Something I work with sometimes is with texts. So you have a lot of different texts, a lot of different documents, and what you do is you compute some statistics of the text. Maybe if you remember, Giordano, if you attended the summer school, winter school, showed you a way of computing embeddings of texts. So basically, convert text into numbers, and you can use this plugin to build a network of similar text. And then communities on these networks become topics, right? Texts that are similar, topics or writing styles. It can become whatever. Again, this is just another way of telling you can build networks in any weird way possible, and that network will tell you something if you are careful in how you analyze it. If you take into account what your edges mean, what your node mean, you can build a network and analyze it. And if you're curious about social media, there used to be a plugin to download posts from Twitter and or follower network from Twitter and analyze it here. Of course, now, if you attended my class on API usage, you know that Twitter costs a lot of money. I looked into it. If you the cost of one tweet is 50 cents of euro, half a euro to just is the price to get one tweet, which means that for a serious study you would need hundreds of thousands of dollars, of euros. So again, nowadays you can do this, but there is another plugin that I installed. It's called Blue Sky, where you can basically Blue Sky is another social network. It's like Twitter. You put here your handle and your password. Handle is the username and your password. You connect, and you fetch your followers, follows, blah, blah, blah. It is something else you can do if you're interested in social media data. And that's it, basically. All the plugins will show up somewhere in Gephi, and you just need to figure out how to use it. But even though it's not very intuitive, Gephi, at times you will find somewhere, someplace where you can actually work with it. So I think I'm done, but we still have 50 minutes. So we could do a couple of things. We could, let me go back to you.
So Andrea, we have a couple of questions.
Yeah, that would be great.
But I have a question for some clarification. So if you would like to use Gephi, your data must be ready to be used, right? I mean, you have to clearly indicate which column is your edges, which column is your nodes.
Yes.
Otherwise, you can't use Gephi, right?
Yes. You would have already to put your data in a way that Gephi can understand. The way I would do it, if I didn't know anything about coding, and if my data is not sensitive, meaning I don't have like personal information of people, I would upload my spreadsheet to ChatGPT and tell it, write me the Python code to convert this into an edge list. So nowadays we have this very powerful tool and we can use it. And sometimes even I do it. I mean, it's easier that way. I mean, Gephi, do you still see my screen, or did I stop?
You stopped it.
Okay. Let me share it again very quickly. One thing, when you go to like import spreadsheet, the way this works is I have this networks.csv file. It is a CSV file that is already formatted like this, like node 1 and node 2. It is separated by commas. So for instance, if I tell it that the separator is something else, it will not recognize it properly, right? So if I say here commas, it will recognize that this is an edge from node 306 to node 0. But if I import it as an edge table, it tells me there is a problem. Edges table needs a source and a target column with node IDs. So I need to go into my file, which is installed here, networks.csv. I need to edit the first line so that this line is called source and this line is called target. Otherwise, it will not import it. This is what I really dislike about Gephi, that importing the data sometimes is tricky. But with ChatGPT, it will help you for sure. So if I go with let me find the network CSV. So you should be able to see now network CSV here. So basically what I would do is I would add a new column, a new row here. I'm not really sure how to do it. Add row below. No. Add row above. And I would write source, and in the other one, target. So this is very ugly, but I save it. And I opened it with the, I hate Macs. So basically I should file. Anyways, I'm not really sure how to, I never use this kind of things. Export to CSV, and I save it. Save. So now what I can do is basically import it from here. Import spreadsheet, and I go into downloads. I think it was downloads, documents. Again, it's a bit tricky sometimes. And I can find my file somewhere. I'm not sure where to find. Called networks. Network edited, this one. Now, hopefully, ecco, bravissimo. Sorry, Italian came out. So now it works. Now it recognizes that these are two columns called source and target, and it tells me, is this a temporal network or not? In this case, it's not a temporal network, meaning that there are no things, there is no time information. So it basically just skips the the time information, finish, and it tells me there are some parallel edges, which means two nodes are connected are connected with more edges. If there are more edges between two nodes, I'm saying sum them. So we will have some edges which will be larger, right? Because there will be more connections between them. And here you see the number of nodes, the number of edges again. You load it. And this is not showing. But yeah, here you see, again, there is this node table, the edge table with all the information. And then here you see this very ugly network that then you can use for SAT+2 to organize. See, way better. See, we have this very huge network and a lot of islands all around. You probably cannot see them all, but this is the idea. Were there any other questions? First of all, did I answer your question? Am I?
Yes,
sure. Was I sharing my screen?
Yeah.
Yes, I was.
Just popped it. Thank you.
Okay.
So,
no.
Hassan asked a question. He is the first one.
Okay, so for beginners, which tab is more easy to
not
use?
That one.
Sorry.
The last question.
Sorry about that. There are a lot of questions. Wow.
If I want to understand networks in a visual manner more than coding.
Yes. Or using code to understand them. What should I do? For instance, understand data collection, especially in social media. Okay, I'm not really sure what you want to do. So let's do it like this. In my opinion, but this is just an opinion, okay, so it's disputable. In my opinion, you understanding networks in a visual manner does not tell you much unless your network is very, very small and you know what you're doing, which are two very big ifs. What do I mean? We have seen some way of making pretty pictures with networks, but pictures, depending on the algorithm that you use to lay out the nodes, the colors that you use, the size, what you tell the size to be, I don't know, I feel that the visualization can be misleading. And so it's hard to understand really something. For me to understand something in network science, unfortunately, you have to look at numbers or distributions, statistics, these kind of things. If you are not interested in understanding really how networks work and the mathematics of it, it's perfectly fine. I would say just memorize a few statistics, just a simple one, the degree, the path, the idea that you can have a path between one node and the other, something like this, the idea of community. And then there are tools. I would use Gephi in your case to input the data and extract the knowledge. So if you're not really interested in network science as a science, so if you're just interested in how can I apply this to my research, which I guess is most of you, personally, I would just use Gephi. If your question is theoretical, which means do I need to learn the differences between directed and undirected networks, multiplex networks, temporal networks, when you say types of networks, something like that. I guess look at the atlas for aspiring network scientists. I will download it very quickly to show you what I mean, and then move on to the next question. Wow, internet is very fast here. So this book has some, where is it? Didn't open it. This book has some chapters, one of the introductory chapters here. How to move it? Wait, something is not working. Okay. One of the introductory chapters here, it will tell you about the types of network. It tells you about the background knowledge, probability theory, statistics, machine learning, but some of these you can skip. You can just look at basic graphs, which is what we have seen today, and extended graph that
Could you
are.
share your screen, Andrea?
Sorry. Yeah, of course I'm not sharing my screen. Sorry, I'm sorry about that. So now you see the screen, but this book, Atlas for Aspiring Network Scientists, you see it linked on the website. It's free, download it for free. I am not affiliated with Michele Coscia, the author, so I just find it to be a very good introductory book. So there is this first section that has background knowledge on probability, statistics, machine learning. If you want to be a proper network scientist, but in your case, if you are curious about the different types of networks, maybe you are curious about temporal networks, I don't know. You can look here, simple graphs. You see there are very nice pictures, very, very, very easy, very few mathematics. Network types, simple networks, grids, and these are, you have properties and explanations, bipartite graphs, what we have seen before, multiplex networks where you have different layers in the networks. Again, these are different hypergraphs. I work with these, where edges do not connect pairs of nodes, but groups of nodes. Again, these are different ways of using network science, and there is a lot of material in this book in a very easy way. Let me go back to where is it? I can't find. Eccolo. So I hope I answered your question. If I didn't, just paste another comment in the chat. I have a project about corporate hegemony. I want to visualize the illusion of choice, consumer thinking, buying from distinct independent community, but all these brand nodes actually connect to one giant hidden parent company. Cool. Very cool project. In Gephi, a good practice to use modularity to color this sub-brand to represent the illusion of separate markets. Citing the hidden parent node based on betweenness, decrease centrality to expose its true monopoly. So I have a feeling. My feeling is that you are already familiar with network science. Otherwise, you're very smart. Or both. Because this is exactly the kind of thing I would encourage you to do. So if you have already this network or this information between the connection between these brands, you could find this information. The key to interpreting what you see on Gephi is, what are my nodes? What are my edges? So what my edges tell me about the nodes? If you think about, let's do it with your example. Your nodes are brands. How are your nodes connected? Are connected because of, I don't know, they are physically in the same store. They are connected because, I don't know, they belong to some particular kind of market. I don't know. The how you define your edges impacts what modularity will tell you later. I do an example that is more close to what I do, simply because it's more easy for me to explain and perhaps for you to understand. Think about social networks. A network, I can build on a social network, I can build a network, a follower network. I follow you on social media, no? I click on follow, and I follow you. There is a link from me to you. And this link means that I see what you post. But I can build another link, another kind of link, that is a comment network. I comment on your post. This does not mean that I follow you. It just means I comment on your post. So you see the type of link that I create tells me what the network will tell me later when I analyze it. Modularity in a follower network tells me about communities of people. Modularity in a commenter network tell me about people who commented on the same stuff, which is not the same thing. So in your case, how you define the edges impacts what you will find. But this is a very good intuition of using modularity and then degree or betweenness or other centrality measures to expose this kind of the monopoly of this kind of. Of course, if your network is all of these companies linked to this parent company, so you have one big node at the center and all a star around it, this is not very informative. You are forcing that. You are forcing that your network is centered about one parent company. So if you could find some similarity, some way of building a network of brands that is not, this is the parent and these are the children, then it would be more interesting. Considering the frequent data limitation in social science research, I like this question. How do issues of data completeness and sampling bias influence? Oh, I love this question. Influence the interpretation of network measures in the computational tools. So this person is asking, given that we have problems in accessing data and we are not sure that the data that we collect is complete, how does this impact the findings? The answer is a lot. So this is true in statistics in general, right? Your conclusions most of the time only relate to your sample, not to the whole population. You have to be very strict in statistics to say that what you see on your sample generalizes to the whole population. You have to do a lot of controls, a lot of tests, right? And even in that case, you will have to have some. You will not have to. Even in that case, you will have to do some, like, stand by some assumption, very strong assumptions. So your question is very good. We have a class on that topic, specifically how the method I use to collect my data impacts my findings. Let me show you, not the class, but let's go on the graph that I was showing you before to show you what I mean. Very, very quickly, because I guess that there are a lot of questions and I don't want to bore any one of you. So this was the question, the network of the mill, right? When we found out that this one guy was the most important person in the mill. So let's say I only know this guy, and I start my data collection from this guy. I go here, and then what do? I have two options. This is an algorithm. I don't want to bore you with the algorithm. The idea is I can go in breadth or in depth. So I can go, I take my node and go all around it in circle to expand, like when you pour oil on the table, you start from one node and then this thing expands like an oil, right? So it goes, it expands. Or you can go in depth. So I take one node and I go through the longest path possible. I don't know how to explain this better, but basically I use a different algorithm to traverse my network. Depending on when I stop, what happens in the network as I collected, and consider it that in social media, while I collected the data, the network is changing, right? I collected the data, but while I collect it, maybe you follow someone else, and I do not store that information because I'm not collecting your data anymore. So data completeness and is very important. There is a very nice paper now that I think about it. I don't know if I should show you this, and maybe it's too boring, but there is a very nice paper that shows sampling bias. So basically what algorithm I use to sample my network, how it impacts my findings, and especially related to vulnerable communities. So if I have a minority and a majority in my network, the way I sample the data, I collect the data where I start from, where I end up, it impacts the findings. And depending on the algorithm I use or how my data is structured, the real data is structured, I have different conclusions. So, but this is a very good intuition that is. Okay, there was also a continuation to the question. To what extent it is methodologically sound to incorporate network analysis and visualization outputs in a poster presentation? I would say it is sound. If you suspect that there is some data completeness issue, you should acknowledge it, of course. Showing a plot of a graph of a network is the same as showing a distribution or a bar plot or whatever. You can lie with a bar plot. You can lie with a histogram. You should not do it. And it is the same with a network. You can lie and manipulate, like use a centrality measure that boosts the size of some nodes that you want to highlight. Maybe these nodes are not really important for your goal, right? So it is methodologically sound to do it, but of course, if there are limitations, you should acknowledge it. For beginners, which tab is more easy to use, overview or preview, to make visualization of the data? Both is doing the same thing in different ways. This is true. So you have to use the overview tab to compute statistics. So this tab, you have to use it 100%. The way I do it is I use the overview to compute the statistics, and then, or to change the layout or something like that. And then I go to, if I want to make like a higher quality picture, I go to the preview one, right? But the overview, you need it for sure. You can also just do like this, right? You can take a screenshot of a network. This will be very poor quality, but now I have my screenshot of my network. But this thing here will give you higher quality in general. It will not, like, especially if you print it in a poster, which will need to be very high quality, you will want to do this with this thing here. But you need to start again from here. What would you recommend to practice what we have learned? This is very good question. In Michele Coscia's book, this one, at the end of every chapter, you have exercises. And the exercises are built on Network X. So now these are not very easy exercises, but maybe here. Now this is a summary exercise. This asks you calculate the number of nodes and number of edges for the graph in figure blah, blah, blah. Okay, so you can do this by hand. You can do this in Python. There are some scripts in the book and some things in this book that you can use. And let's just very briefly go over. You see, it's 900 pages book. So there is a lot of stuff in here. Some things that we have not covered, but for instance, you see here we have degree, paths, centrality, some centrality measures, generating synthetic graphs with some characteristics, epidemics, complex contagion, link prediction to predict new links, filtering the network when you have noise, homophily. There is, again, a lot of things, communities. graph mining is using basically deep neural networks to understand the graphs. Holistic network analysis, I'm not even sure what that is. And then there is some visualization as well. So there is a lot of stuff in this book, some application, data and tools. Again, this book is very complete. And it helps that it's very easy, and I don't have time to show you how it is written, but just to tell you how simple it is and how friendly it is. Sometimes there are pictures of cats for no reason. So when you're tired and you're flipping through the page and you see a picture of a cat sometimes. So the guy used very simple language to explain stuff. Okay, so there aren't other questions, I guess. But if you have any other question, you find somewhere here. This is actually my website. You find some links to my email, and you can also find my email here. So whenever you have some questions, you want to work on something together, or you just need guidance, and I can just point you in the right direction, I would be happy to just know that you are using these tools to do something in your research. Maybe these things are useful, maybe they are not. I encourage you to try and understand what network science can do for your research. I don't know if you have any other questions. Where is it?
I guess no one has a question.
Okay. That's great. So I think I think we can close here. If you, Sumaya, if you agree.
Sure,
Again,
sure.
my goal, I know that I have overwhelmed you with a lot of stuff, a lot of ideas, a lot of measures, mathematics. There were some mathematics, code, and then Gephi, and doing the same things in different ways with Python and with Gephi. I know that this is too much sometimes. I know that this lecture is very dense, but again, I hope that by bombarding you with a lot of random information, hopefully I've shown you the power of networks and how you can use very simple measures, very simple ideas to generalize across contexts, to apply tools from biology to linguistics, tools from linguistics to political science, and so on and so forth. So again, if you have any questions anytime, feel free to reach out to me or to Sumaya, who will link you to me. And thank you very much for attending this late in the afternoon, and have a nice weekend.
Thank you very much, Andrea. I hope we will be seeing you in the summer school.
Sure. I hope so too.
Thank you very much for the participants as well. So you are having hearts and
yeah. Thank you very much.
yeah.
So I tend to get very emotional, so I will get out of the call before I start to cry. Okay, I'm not joking. So yeah, I really like this YADESA project and the people that it's bringing together.
Yeah.
So
Alright.
see you hopefully in the summer.
Yeah.
And thank you, Sumaya, for organizing all of this.
Thank you for
See you.
attending for this fascinating session. Hope to see you, and thank you, everyone. I will see you in the next session.